everyone, welcome back to DentChem. Going to be talking about something super important today. Identifying electron-rich and electron-poor sites. So if you've watched a lot of DentChem already, you're going to hear me ask all the time, who has electrons and who wants them? It might be one of our most important questions in OChem. This is where it all originates. This is going to help us identify where to draw reaction arrows a lot. It'll really help us out in mechanisms, okay? Identifying electron-rich and electron-poor sites. I've included a periodic table up here, a very small one. This is really our organic chemistry periodic table. 95+% of the time, we're only dealing with elements right here. The main thing we need to understand for identifying electron-rich and electron-poor sites, we're going to use this electronegativity trend in the periodic table, something hopefully we've already gotten from general chemistry, okay? Electronegativity increases as we go right and as we go up the periodic table. Fluorine is our most electronegative atom. So if you just remember one thing, remember fluorine. Most electronegative all the way on the top right. We're also going to throw in a little separate rule here, very minor, but remember, double bonds, carbon-carbon double bonds are electron rich. So we're going to see those act as nucleophiles later on, okay? So just going to throw that in there. It's really mainly one rule. We'll just say it's two, but even so, condensed down into two rules. This extremely helpful tool we're going to use all years long, how to do it, in really two steps, okay? Electronegative trend. If I have two atoms and one is more electronegative than the other, more electronegative, less electronegative, this is going to be electron rich and this is going to be electron poor. Electronegative atoms are going to pull electron density towards themselves, okay? When they do that, they pull that negative charge towards themselves and they leave a positive charge in that place. Let's go ahead and show that in these examples right here. I look at this molecule here and I notice that I have a different bond and different atoms bonded to each other, okay? So there's going to be a difference in electronegativity. This carbonyl bond, this carbon double bond to an oxygen, might be the most important bond in this year of organic chemistry. First, let's identify which is more electronegative, carbon or oxygen. If I look at the periodic table and I know my trend in electronegativity, I should know that oxygen is more electronegative than carbon. To show that, I am going to give oxygen a partial negative charge. That's showing that it's pulling electron density towards itself. And that the carbon it's pulling electron density from, then we'll get a partial positive charge. That's pretty much it, okay? Really important bond, we're gonna see it all the time, okay? Let's get some more practice here. I have this carbon chain, okay, butane with a couple fluorines on the end, okay? Our fluorines there, really electronegative, right? Really electronegative. They're pulling electron density away from that carbon they're bonded onto. So they're going to get that partial negative charge to show that they are electron rich. And my electron poor site will be the carbon they are bonded to. All of this is spatially relative. If I had a carbon, if I had this carbon chain extended across the board, all the way up here, this carbon all the way up here would hardly be affected by these fluorines at all, okay? The carbon right next to it, that's where they're really pulling from. So it's going to be affected the most, and maybe a little less here, and by about 2 or 3 bonds away, there's really no effect, okay? So that carbon that they're bonded onto, that's why we put the positive charge right on that carbon. I'll look down here, I have a Lewis acid, AlCl3. We're going to see this a little bit in the future. I look up here, which is more electronegative? Chlorine's a lot more electronegative than aluminum. So each of my chlorines will be electron rich. They're going to share and they're going to pull electron density away from aluminum, leaving aluminum with a large partial positive charge. There we go. Last example here, I have a carbon double bonded to a nitrogen. I look at my periodic table. I know that nitrogen is slightly more electronegative than carbon. Electron rich. And then that carbon, in turn, electron poor, and it gets that partial positive charge. All right? Now the difference in electronegativity, maybe here, is not as great as it was with carbon and oxygen. Notice the difference in electronegativity for carbon and oxygen is greater than that between carbon and nitrogen. So even though we can still identify this as electron rich and electron poor, but we can also compare different functional groups to each other using that one rule. Lastly, I see a double bond there. Alkenes, pi bonds on alkenes can act as nucleophiles. Put simply, they're regions of electron density, electron rich, and we can put a little partial negative on our alkene as well. Okay? Where this comes in, why this is really important, later on we'll get mechanisms in here, and we'll have what we call nucleophiles. Okay? And nucleophiles are really electron rich. Nucleophiles, they love to attack the nucleus. Opposite charges attract. Okay? So I have a nucleus with negative charge. That negative charge is going to want to attack a positive charge. And because we've identified where those positive charges are going to be located in our molecules, we can predict where our nucleophile is going to attack. I have a nucleophile here with negative charge. It's going to attack areas of positive charge. So we would expect our nucleophile to attack this carbon here, and it would likely attack this carbon right here. It might attack this aluminum right here, and it might attack this carbon all the way down there. This is going to be a bulk of mechanisms. Who has electrons and who wants electrons? Negative nucleophile attracted to positive electrophiles, or regions of positive charge regions, partial charge, that we've located now that we understand how to identify regions of electron density. If you'd like some more practice, I have some here on the back, of which I already solved one by accident. So yeah, I just a little bit of help there. So if you want some more practice, I'm going to link a video on me solving these. Work on your own, and then we can see where we can improve. Like this video, please. Subscribe to the channel if you haven't already, and keep supporting DentChem. Thank you for your support.